name is Thomas Slimak. I'm from the Technical University of Munich, and I'll be talking about Lola and the forbidden fruit, also known as development of direct drive actuators for humanoid robotics. So, the first question is, who even needs direct drive? Why do we even care about it? So here you can see a simulation of Lola, where she's walking around some obstacles. And our friends from MIT will say that this doesn't look particularly typical or normal. That we can see the steps are quite small, that the gait is kind of stubborn, and that the steps being taken don't really exhibit any type of swinging as we expect from a human. So the question is, can we add these characteristics somehow and get all the benefits that humans also have during walking, which includes speed among other things? So in order to do this, what I'd like to do is develop new legs for Lola. And this involves developing flexible controlled legs, where the keyword kinda. So we don't want fully flexible legs, we don't want spaghetti legs, we just want flexibility in some very special localized areas, such as parallel to the motor or in series with the motor to help with the impacts during walking or to support the motors while they are having to exert forces in certain directions by preloading them through elastic elements. In order to do all of this, we need a flexible multi-body simulation of the robot. So that's what I'm currently working on, and this then allows us to see how big are the deformations, are they really linear, are they non-linear, can we account for them somehow during modeling and planning of the dynamics of the robot. We see some preliminary results of what the deformation of one of the components might look like. But in doing this, we saw that we have this problem, that we have these harmonic drives in there, which obviously also have some flexibility and dynamics. And how do we account for this in our modeling? So we tried all different kinds of fancy things that include data-driven approaches with neural networks. And these harmonic drives, they just do whatever they want on the inside. So they're flexible, they're sometimes not flexible, it depends on temperature, who knows what's going on. And that leads to these large inefficiencies. So maybe for those of you that don't know what harmonic drives are, they are gearboxes that are located at the end of each of our motors to include this high gear reduction that's necessary to turn our high-speed spinning motors into high torques at low speeds, which we need for our locomotion. And this high gear reduction introduces then all of these very difficult to model effects that also then influence the dynamics of our system. Other disadvantages of these harmonic drives are that they're relatively expensive and they're also somewhat fragile. So they include many very small teeth, and you can imagine if you have small teeth on a flexible spline and you then impact the entire system, as would be the case if we're trying to run or jump with the robot, these little teeth can come out of engagement and jump over each other, which isn't great for the teeth, and it's even worse for the control engineer trying to do something with that. So we somehow like to get rid of these harmonic drives. Another reason is that we want maybe to also include this stiffness or swinging of the leg, and one solution could be, don't do it with mechanical systems, do it all virtually. Just model your spring or model the swing stuff and then just control your legs so it exhibits the behavior as if there was some virtual stiffness. The issue with this is that it always relies on a relatively high controller bandwidth, which isn't easy to implement always. So the solution, let's sidestep this entire issue and just not use any harmonic drives or transmissions and just build a direct drive motor. So the type of motors that we're looking into here are called axial flux motors. So they're different from your typical radial flux motors in the direction in which the magnetic flux lines go. So in a typical radial motor, the magnetic flux lines deviate out radially from the rotation axis, and then in a normal axial flux motor, they are then parallel to this rotational axis. And then here you can see two different arrangements how this could be built. The reason we want the magnetic flux in this direction is that it allows us to use the Lorentz force, which then enables relatively high torques. So what we want to do, we want to build this motor, but before we can build anything, we have to simulate it. So in order to simulate it, we create a magnetic simulation using ngSolve and NetGen, and it then uses the Maxwell stress tensor to calculate what is the torque. Obviously, we don't just trust the simulation, so we validate it by measuring the force on two magnets opposed to each other, or a coil and a magnet, move them apart, and we see that we're able to get relatively good results, sometimes a bit worse, but they're around 10% normalized root mean square error. So we can trust the results, but we have a bigger issue, namely the size of the simulation. So to get accurate results, you need extremely large simulations, and that means that we need to employ some different forms of reduction, but this is quite easy here because we have a symmetrical system. We also know that we can do some interpolation and extrapolation of parameter effects, and after doing this, we're able to reduce the simulation so it runs in roughly 5 minutes to get the maximum static torque for one configuration of motor design.
What's with those 8 million?
For the differential equation, there's 8 million. Sorry. So we have this, then we can do various parameter studies to see what is the effect of different design parameters on the torque. So we see that there's a flattening off of the maximum torque you achieve as you increase the depth of a coil, or also different arrangements of coils. So you can imagine the layers can have different offsets in the stator between each other, and this then generates a somewhat smoother torque profile, so you don't have this torque ripple as you spin the motor around. We do a bunch of testing here, and we can kind of hand-tune the parameters, but what's much better is using some type of automated system. So we create a cost function that includes all the things we care about, like the mass, the torque, the volume of the entire thing, and then we give it all to an evolutionary algorithm, let it run for 24 hours, and then we're able to see that we're able to come up with a design that meets all of our specifications that we wanted. So obviously there's an endless number of improvements you can make to the simulation to make it more accurate, but at a certain extent you need to test it on a real system, so that's what we're currently doing. We're building the actual motor, adding some flexible elements that we can put strain gauges onto and then measure what the real torque is, and if we're able to actually accurately control this torque, and if that all works, we'd like to build these into Lola. So thank you for listening to my presentation.
Is that 50 newton meters peak or 50 newton meters continuous?
Continuous.
Okay. Do you have any idea of how much the mass of the whole motor would be?
Yes, and I left it out intentionally because it's not particularly good. In this case here, it weighs roughly 3 kilos, so 3 to 4 times more than the equivalent radial motor that we're currently using. But this is more to do with the design of being completely optimal and us not including all the possible design parameters so that it runs fast enough. It's definitely possible to do it better. Yeah?
At the beginning, you showed your position control robot and
Sure.
how it looked not good.
Yeah.
Why do you think you can't improve that?
So it definitely would be possible to improve it, but I think the improvements would also require some pretty complex control, and I think that's easier when we have these direct drive motors and we do torque control for the swinging motion.
Why do you think that?
Well, because I can just let the legs swing. I don't really have to control what it's doing and then let it land in front of me.
But with position control, you can say leg angle equals sine of t, and it will look like a swinging.
Yeah, I can have the swing, but then I also have this interaction between the hip joint and the leg, where I have some force happening, unlike when it's swing, where it just freely moves forward.
Okay.
Okay. Yeah?
You went through it pretty quickly when you said we're comparing the axial versus radial motors. So you briefly said like high torques.
Yeah.
I'm wondering like, there might be a reason why axial is not used. Like what is the advantages or disadvantages of using axial?
So it's actually a very interesting story. The first motors that were ever developed were axial flux motors, but then they were given up on for very particular reasons or peculiar reasons that they said they were too expensive to manufacture or difficult to build, whereas I think the coils being used in radial flux motors are often very complex, so these winding machines do all kinds of gyroscopic motion to achieve the winding they desire. And we're seeing a development of these motors now being used more and more, so especially from the Asian space. There's many research papers coming out where they're using these for robotics. There's even an exoskeleton that's trying to use these with some moderate success. Yeah.
So one of the ideas you have is to move towards more direct drive actuators. And so this will be coupled with a smaller gear ratio.
Ideally none.
And then you want to also add the torque sensor
So
after. You cannot use...
So there's two problems there. One is just to validate that we're really getting the torque from the current that we expect. And the second problem is back EMF, right? So just because you're measuring this current doesn't necessarily mean it's the same torque. And it also changes based on the arrangement of magnets and coils to each other because we have these gaps in between it. So it's just a test for now. Yeah, do I have to finish?
Yes.
Okay, but no one else is here.